Explain how to do prime factorization. To simplify radicals. Prime factorization is factoring out values to get down to their prime numbers. So factoring is dividing out. So if I were to take the number 20, the prime factorizations, or even just if I just want to talk about factorization, factoring is figuring out what are the factors of 20. So I know that 1 in 20 will multiply to 20, 2 and 10 will multiply to 20, and 4 and 5 will multiply to 20. This is just factorization. Now, prime factorization is finding these numbers that will go down that are just prime numbers. Because I know that 4 times 5 here will give me 20, 2 times 10 gives me 20, and 1 times 20 gives me 20. So if I write them out as prime factorizations, I want to start with prime numbers that will go into 20. So the first prime number is 2, and 2 times 10 will give me 20. Now 2 is a prime number, but 10 is not. So I want to drop 10 down to as prime as possible. So I'll drop 10 down to 2 times 5. 2 is a prime number, and 5 is a prime number. So prime factorization shows that 2 times 2 times 5, which is the 2, and the 5, that these are the three numbers that are all prime that will multiply to 20. This is what prime factorization is. So in order to use this to simplify radicals, I'm going to write it out as the square root of 20, and I want to simplify this using my prime factorization. So again, I know that my prime factorization is 2 times 10, and 10 can keep going, so 10 is 2 times 5. So I have that the square root of 20 is the same thing as the square root of 2 times 2 times 5. Now the reason we do this is because we have a pair of 2's here, because this would give us a perfect square. 2 times 2 is 4, which is a perfect square. So what we do here is, because we have a pair of 2's, when I take these, the square root of these pair is 2. But that means that we're going to bring the square root to the outside, so we're going to have 2 on the outside. Because we have a pair of 2's, we can bring one of the 2's on the outside, and the other one just goes away. But the 5 does not have a pairing, so it's not a perfect square, it's just a 5, so it stays on the inside. So the square root of 20 is equal to 2 square root of 5. And the decimal value for each of these are the same. So prime factorization is writing out the factors, what multiplies to give you the number, all the way down to its prime values. When we're using it to simplify radicals, we do this so that we can find the pairings of any numbers so that they give us a perfect square, which is what a pairing is. So 2 times 2 is the same thing as 4, which is a perfect square. This is also can be written as 2 squared times 5. This means the same thing. So that's why we can take the square root of 2 squared. And that's why the 2 becomes to the outside. It's called the coefficient. And the 5 stays on the inside because it does not have a pair. It's not a perfect square. So the 5 stays as your radicand, which is on the inside of your radical. So another example, if I give the square root of 54, and I want to simplify this using prime factorization, I have to know what the prime factors of 54 are. So I'll use my deductive reasoning to know that this is an even number. I can divide by 2, and 2 is a prime number. It is the only even prime number. So 2 goes into 54 27 times. So I know that 2 is prime, so that one's finished. I'm going to use 27 and see what multiplies into 27, which I know is 3 times 9. 3 is a prime number, but 9 is not. I can continue using 9 as 3 times 3, and I get both of these are prime numbers. So the square root of 54 can be rewritten as the square root of 2 times 3 times 3 times 3. I can write this out this way so that I can find any of my pairings. And I do have a pair of these. Now I have 3 3's here, but you can only do groupings of 2 because we're dealing with the square root. This tells us that we want groupings of 2 numbers that are the same. So this 3 and 3 here, that is a pairing. So I could technically rewrite this as 2 times 3 times 3 squared. I still have 2 here, and I still have another 3 here. Or sorry, I have 2 3s and another 1 3, so I still have 3 3s, which is what we have here. So the reason I do this is this 3 is allowed to come out to be a coefficient because I'm taking the square root of 3 squared, which is just 3. And then on the inside, I'm left with the 2 times the 3 on the inside. So I can simplify this to become 3 times the square root of 6. And that is equal to the square root of 54. And these will have the same decimal values. You do have to recognize, so if I do the square root of 144, you do have to recognize when you do have perfect squares before you do any factorization, because perfect squares are automatically square rootable. So I take the square root of 144 is automatically 12, and we don't do any decimals there. There's no more radical left over because square root of 144 is perfect. This is 12 times 12, and the square root of 12 squared is equal to 12, which is why there's no more radical left over. So the square root of 144 is equal to 12 with nothing else remaining. So if I do one more, the square root of 2,520. This is a little bit bigger, but I can still use my knowledge of how to divide numbers. I want to know that this is an even number because it ends in a 0 or an even number, so I know I can divide by 2. So 2,520 divided by 2 is 1,260. 2 is prime, so I'm going to stop on that one, but 1,260 is also even, so I can divide that by 2 again. You can always use larger numbers to start with if you didn't want to use 2. I'm just using 2 because I know that they're even and I know that 2 is prime. So 630 is also even, so I can divide that by 2 as well. And I get 315. So 2 is prime. 315 is not even, but it does end in a 5, so I can divide that by 5. And by the way, I could have divided this number, 2,520, by 5 because it ends in a 0. I could have easily done that first. So if I do 5, that's 63. So 5 times 63. So 63 is going to be, it's a multiple of 9. So that is 7 times 9. So 7 is prime, so that's good. 9 is not prime yet. 9 is 3 and 3. 3 is prime, 3 is prime. So once I have no more numbers to factor out, I have all of my prime factorization. So I can rewrite this as the square root of, and I'm gonna try and put the numbers in order. So I have a 2 times a 2 times a 2. So I'm gonna check those off because I've used those. I don't want to double them up. Then the next values are, I have a 5 here, but I do have 3s down here, so I'm gonna put those next just because those are numerically in order. 3 times 3, so I've used both of those 3s. Then I have a 5 and a 7. And if you were to plug this in, if you do 2 times 2 times 2 times 3 times 3 times 5 times 7, you get 2,520. So I want to simplify this, and I look for, again, since this is a square root, I want to look for groupings of 2 numbers that are the same. So I have a 2 and I have a 2 here. I have another 2, but I don't have an extra one, so this one is by itself. I have a 3 and then another 3. Then I have a 5 without another one, and then I have a 7 without another one. So that means that I can simplify this group, and I can simplify this group. So when I simplify this, I bring one of the 2's to the outside, and then I've simplified this section. I keep this 2 on the inside because I didn't have a pair with it. I have this grouping of 3, which means I'm allowed to bring that to the outside to the coefficient. And it's all multiplication. Everything is multiplication throughout. So I still have that 2 times that 3. Then I have the 5 couldn't go anywhere, so I'm going to keep that on the inside with the multiplication. Then I have the 7, again, also on the inside with the multiplication. So now I have everything in its correct location, and now I can just simplify. So the coefficient, the outside is 2 times 3, which is 6. I have the square root symbol. Then I have 2 times 5 times 7, which is going to be 70. So my prime factorization of the square root of 2,520 simplifies down to 6 square root of 70. And that is my final answer.